there, Vanessa Schneider from Google. I'm excited to kick off the Crisis Response Lightning Talks. I'm here with an amazing and inspiring group of people using geotechnology for good. We hope these talks will inspire you to think of new ways that you can have an impact with mapping tools. All right, let's get started. So first up, we have Sander de Haas. Sander is the co-founder of SamSamWater and a landscape restoration expert at Just Dig It. Sander is trained as a hydrogeologist and civil engineer and has a lot of experience in water and landscape restoration programs throughout Africa. Sander combines practical insights from the field with innovative uses of technology to support humanitarian aid workers during crisis response efforts and refugee camp planning. Welcome, Sander.
Thank you, Vanessa. So during this talk, I want to explain I want to show you some examples of how we use open data during crisis response efforts. And here I'm specifically aiming at humanitarian aid workers without GIS experience. For example, people working out there to evacuate people or to provide drinking water to refugees. So for the first case, let's focus on something that's happening at the moment, the volcanic eruption at La Palma. Lava flows are threatening houses and damaging infrastructure. And this is how La Palma looks at the moment on Google Maps. You see an indication that there's an event happening, and that's already very useful. But if you zoom in, you see the base maps haven't been updated yet, which is understandable. So you don't see the extent of the lava flow. Well, if you are interested to see more, luckily there's websites like the Copernicus Emergency Management Service where you can download daily updates, KML files showing the extent of the lava flow. So let me switch to Google Earth to show you that. So this is the lava flow, which you can download from that website. And if you look at it in 3 dimensions, it really helps to give you an insight in the situation. So where are houses under threat? Where's infrastructure damaged? So this is already very useful to get this extra layer of information. But then I'm a hydrogeologist, so I'm always interested in subsurface and soils, since that often provides a lot of context and background and can direct you towards solutions for problems. So that's why I added this layer showing the geological map of La Palma. And then you see that this recent lava flow here in black, it's not on the geological map yet, it's understandable. But there are many other lava flows like that happened in the geological past of the island, and they actually shaped the island. And that's very useful to understand the context and to seek for solutions. For example, if you want to know where you can drill for fresh water after such a crisis event, it helps to understand where these lava flows are. You can't see them on the satellite image, but by just combining several layers of information, lava flow and all the geological maps, they provide that extra bit of context. Well, this is an example from La Palma. It's a Spanish island, it's very well mapped, and this disaster gets a lot of attention. But there are many other disasters in areas that are well less mapped, and where geodata can help to create insights in the problem and potential solutions. So for example, let's look at this event. Back in 2019, Cyclone Idai hit Mozambique, Zimbabwe, and Malawi and caused huge floods. So imagine you're being sent out there as a humanitarian aid worker. You have to rescue people, for example. The first thing you do is you look at Google Maps, and this is how the area looks on Google Maps. There's actually not much to see there. It's not so well mapped. So that's why I developed this web viewer and added this base map. It's a very old base map developed by the Soviet military back in the Cold War era in the 1980s. So it's an old map, but still provides a lot of details on the landscape, where are the swamps, where are the river arms. Provides a lot of context, which is still useful to date. And then another layer is this digital elevation model showing more information about the topography, where are the high areas, where are the low areas, helping to understand the landscape again. And then I found this GeoTIFF layer, a satellite-derived flood extent map. Easy to use if you know how to use GIS software. GeoTIFF, you can just visualize it. Only a lot of humanitarian aid workers don't know how to do that or don't have the time or the internet connection to do so. So I added that to our web viewer to show people the extent of the flood. So which infrastructure has been damaged, which roads might still be accessible and which not. And then another layer was a download from OpenStreetMap, the buildings there. So all these red dots indicate buildings or houses. So you know where the settlements are, and you can identify where areas where people might be trapped in their houses and in desperate need for relief efforts. So this shows that just a simple combination of layers by old data which was already available can help to aid people that are providing relief services if it's made in a way that's accessible to them. So another example that I worked on is this refugee camp, Tendeli refugee camp in Tanzania. And for that, I switch back to Google Earth. This is where the refugee camp is located. And if we zoom in, we see the refugee camp here, all the small tents. And then there were a number of boreholes of the camp and the storage tank in the camp itself. And if I toggle to 3D mode, and especially if I add the elevation map, some colors, you see that the boreholes are down here in the valley, and the storage tank is at the high point in the camp itself. And there was a pipeline connecting these boreholes to the storage tank. And just by visualizing that in an elevation profile, you can understand why some of these problems were occurring. So the water was being pumped from this borehole, had to be pumped down in the valley before it was being pumped up this hill. And at this low point here, there's a risk of siltation, so sediments being trapped in that pipeline, causing blockages and malfunctioning of the pipeline. And then the water had to be pumped up over this hill towards the reservoir tank. And again, this hill here is a risk where bubbles of air or pockets of air might get trapped in the pipeline and causing so-called air locks. So another risk of malfunctioning for the pipeline. So just by visualizing the data which the field officers had, was able to identify possible problems and come up with solutions. So by just playing around the pipeline, it was sloping up much more gently without the risks of siltation and air loss. So again, this shows that by combining knowledge from the field with geodata, we can easily understand what the problem was and how to solve it. So these were just a few examples of how combining data sources can help during crisis response efforts. And there's so much data out there. So let's make sure that we visualize it and make it available in such a way that it's easy to use for people that work out in the field, those people that save lives and protect the environment. And at the moment, we are working on a map toolbox where we bring together map layers that are useful for crisis response efforts. And I hope to show you more on this during the next Geo for Good Summit. We're still looking for partners to further develop and trial this in actual crisis situations. So if you're interested, please reach out to me. Thank you.
Thank you so much, Sander. Next, I'd like to introduce Yifang Ban from the KTH Royal Institute of Technology in Stockholm, Sweden, where she is Professor Director of the Geoinformatics Division. Yifang's research is focused on multi-temporal, multi-sensor remote sensing, Earth observation, big data analytics, machine learning and deep learning, and their applications in global environmental change monitoring and climate change-induced disaster management. So excited to have you. Welcome, Yifang.
Hi, everyone. I would like to tell you about our research on AI-enabled wildfire detection and monitoring with multi-sensor EO data. I'm Yifang Ban from KTH. As you all know about IPCC recent report, it's code red for humanity. Climate change is widespread, rapid, and intensifying. There are many humanity facing many challenges, from melting sea ice to drought to flooding to wildfires. Wildfires has many human and environmental impact. It damage property, infrastructure, kill displaced people, cause billions of dollars to fight, cause loss of habitat, increase carbon emission, pollution, and soil erosion. With the launch of many Earth observation satellites, it is possible to detect wildfires early and monitor wildfires in near real time. So here the example on the left are GOES-R images every few minutes, you have an image. It's possible to detect active fires as early as possible. On the right are VIIRS, day and night images. You can also see the hotspots very well. The current wildfire products, including monthly modest burned areas, but these are not near real time. It's a monthly average. So for near real time detection monitoring, these products are not very effective. We have VIIRS daily active fire products. These are on the daily, and it's very useful for emergency services. However, there are many false alarms. So here I show example of some false alarms detected for Dixie Fire, the largest fire in California this year, second largest in California's history. So we have used a deep learning framework for early detection of wildfires using GOES-R time series. The results are quite good. So we are able to detect fires as early as possible, sometimes earlier than the VIIRS wildfire detection time or than reported time. So this is very significant. So if we're able to do this on a global scale. And for near real-time progression monitoring, we've been using Landsat, Sentinel-1 radar, and Sentinel-2 optical images for the early detection and monitoring. And so here are the examples of the 2021 Lytton Spark Lake wildfires near Kamloops, and also the 2021 Dixie fire in California. You can see both radar and Sentinel-2 and also Sentinel-2 image are able to show the wildfires very well. So we have developed 3 different frameworks for near real-time wildfire monitoring using EO time series. On the left are the 2 work that I presented already during the summer, the crisis response seminar. It's a continuous joint learning versus learning without forgetting. They're already published, paper 1 and paper 2. The new work is using total variation regulated transfer learning. So this is the 3rd paper we have just submitted. So the transfer learning has a lot of potential because we have many past fires we can use to train our deep learning model and then do the prediction on the ongoing wildfires. So I'd like to show some results. So these are the results from the Creek Fire from 2020. So we can see that the near real-time progression is captured quite well. And this is another example. We in a different environment, Fraser Island fire in Australia. So again, we were able to capture the progression very well. And then we also tested in this year's Dixie Fire. So on the left side, you have the VIIRS progression result. It's a coarse resolution at 75 meter resolution. On the right is Sentinel-1, Sentinel-2 monitoring at 20 meter resolution. We have much more precise detection and also a lot of details. And you can see on the top that VIIRS have missed some detection, and Sentinel-1, Sentinel-2 has a complete monitoring. And then we overlap this on the Sentinel images. You can see more details where we detected they were in an unburned area, but VIIRS detected as burned areas. So these are mainly using images from Google Earth Engine. So we have developed 2 Google Earth Engine apps. One is for British Columbia on the left, and on the right is for California. So you can see the progression. You can also see the active fire points as well. So the results are very good.
Thank you so much, Yifang. And next, I'd like to introduce Ariana Mercer from CEDR Digital Core. Ariana is the mapping team lead at CEDR, as well as a GIS analyst for Union County, North Carolina. She's passionate about emergency management, cartography, and fluvial geomorphology. Great to have you with us, Ariana.
Great to be here. During a natural disaster, situational awareness is crucial for officials and individuals to make informed decisions. There are many tools we can use for situational awareness, but one of the most powerful to communicate the scale and scope of disasters is imagery, photos, and videos. The Civil Air Patrol is a volunteer organization that serves as the civilian auxiliary of the United States Air Force. One of their missions is emergency services, including carrying out search and rescue missions, disaster relief, and humanitarian services. The Civil Air Patrol, or CAP, provides aerial imagery to aid emergency managers in assessing damage during and after natural disasters, such as hurricanes and wildfires. This image shows a photo of Alexandria, Louisiana, after Hurricane Delta last year. We brought the images into Google Earth Studio, so you can see the Google Earth imagery behind the CAP photo, and you can notice how the field that you can see in the background turns into a pond in the photo. So you immediately see the difference before and after the storm. What we're aiming to do at CEDR is bring these images into Google Earth using Earth Studio to create animations that allow you to essentially fly over an area and see not only the Google Earth imagery, but also the Civil Air Patrol images on top of that. This will allow you to see before and after images, so you can easily see flooded areas, damaged buildings, or whatever kind of damage the storm or wildfire has left behind. We hope putting these photos in context will allow them to be used more widely. CAP photos are a great resource, but it can be hard to sort through the large quantities of photos to really get a clear picture of what's going on and where. We hope by making a more user-friendly end product, the Civil Air Patrol photos can be utilized more widely. So CAP images provide latitude, longitude, and altitude for each photo. However, they currently lack metadata on the camera's orientation, so we do have to manually match or georeference each image in Google Earth. These are oblique images taken from the CAP planes, so they're not a traditional aerial image that you might think of that's looking straight down on the Earth. When you think about the position of a plane in the air, it can rotate in 3 directions. You've got the X, Y, and Z axes. And so you could potentially have photos with the exact same lat long and altitude, but have that camera pointing in completely different directions. Matching these by hand can be challenging and time consuming. So we hope future releases from the Civil Air Patrol may include more metadata about the orientation of the camera. And the photo you see here is a CAP image from Hurricane Ida just a couple months ago, overlaid onto Google Earth imagery. And you can see it's not 100% match between the photo and the Google Earth imagery, but it's close enough that you can spot the differences easily between that base imagery in Google Earth and the photo from CAP. We're using Google Earth Studio to not only bring the images in, but then also to create animations that allow you to virtually fly over a community and quickly see the areas where you might need the most resources or areas that have been hit the hardest versus those less affected areas. Essentially, the idea is that you're following the flight path of a plane that took the photos and getting the same kind of bird's eye view that the pilot would have gotten. But you have the advantage that you can pause the animation and take a closer look at any of the images. This allows you to get a quick overview of the conditions throughout a community, which is important after hurricanes when many roads may still be impassable. And you may be more heavily reliant on this aerial imagery versus going out and doing ground surveys. And the image you see here is another image from our animation of Hurricane Delta in Louisiana. And you can see the background image, you again see some fields, and then in the photo, you can tell that those are quite flooded. Our Google Earth work is just one part of what we do at CEDR in response to natural disasters, which includes mapping wildfires on NAPSG's Fire Mappers map, CEDR's own shelter map, and our continual work on social media to amplify and clarify evacuation orders and other essential public safety announcements. And this is one last image from Hurricane Delta last year, transitioning from Google Earth imagery to a cat photo. And this actually shows the same area of flooding as the last photo, just from a different angle. And that's all I've got today. Thank you, and I look forward to your questions and hearing from you if you'd like to know more or to learn about potentially joining CEDR as a volunteer yourself.
Thanks so much, Ariana. Next, I'd like to introduce David Saah from the California Energy Commission's Pyrogens program, focused on building the next generation of wildfire models. In addition to this work, David has more than 30 years' experience collaborating on a variety of wildfire research and application efforts. Great to have you. Welcome, David.
Hey, thanks for the introduction, Vanessa. So what we're going to talk about today is how do we scale wildfire intelligence for impact? And so when I'm thinking of impact, what I'm really thinking about is the first question that comes to mind is like, what is a wildfire risk? And I break that out into two different sections. Break it out into trying to understand what a wildfire hazard is and the vulnerability. And on the hazard side, I'm thinking about things like the likelihood, annual burn probability, thinking about things like intensity, flame length. On the vulnerability side, I'm thinking about things like exposure. How long is a building actually exposed to a flame length of a certain duration? And when exposed, I'm thinking about susceptibility, how much damage is going to occur. And so these are all, when you think about all these sorts of questions and all these sorts of different elements that go into risk, it's a complicated information flow to make all this stuff go together. So how do people typically do it? First thing that people typically do is that, there's a generic assessment process. First step in that assessment process is really trying to get an understanding of the things that you care about. What are the highly valued resources or assets? And they could be both natural and character, people for sure, a human infrastructure for sure, and interplay between them. Once you have an understanding of what that is, the next step is to go into and identify wildfire simulations and how it interacts with that. From that, you move into exposure analysis, and then from that, you move into effects. There's a logical flow for this. This flow has been documented for a while, as you can see from this 1990s graphic, where you have a bunch of different data and information flow from each of those different steps and how they all fit together. Think of this as a bunch of information flows that we need to tie in. And as more information comes through the pipe, we need to be able to expand this stuff, right? And so the first challenge that we see is like when we're thinking about where to do it, where do we do these sorts of risk assessments? Where do we need to collect information? Where do we need to pay attention? The first thing that folks typically think about is like, well, where are the places that typically have fire? Right. And so again, that bit of information is key and critical to a lot of the stuff that we're actually thinking about and doing. And if you look at some of the data sets that we have, some of them go back to the 1800s, and they're poorer in quality but rich in history, to stuff that's more current right now that gives us really detailed progression information that's important to this conversation. Next thing that we think about is, where are the people on this landscape? That's one side of the equation. And you could use a variety of different information products to help us identify what they are. Some of them are Earth observation based. Some of them are more field based in character. But the places that we really care about aren't necessarily the bright, yellows and whites in this graph, but it's those places that are more those rural areas, right? And trying to get a characterization of what that wildland urban interface is and where folks actually are located. Because these landscapes are complicated, and they're complicated in a whole kinds of different dimensions. They're complicated in terms of the types of treatment activities that have been put on the ground already by both state and federal agencies. They're complicated by the fact that you have a bunch of private sector folks and local municipalities that are putting in treatments, not only now, but over time, with a whole variety of planned activities associated with it, and they all need to work in concert. In terms of trying to understand wildfire risk. And there's a couple different approaches in thinking about this thing, in terms of trying to take all those different configurations and put them together. One approach could be like a top-down approach. A top-down approach in terms of actually using national data sets and national databases to identify the potential wildfire risk to community housing units, right? Which houses are most at risk based off of some common standards that are normalized across large regions. Nice thing about this is it gives a pixel-to-pixel comparative analysis that can be used for a lot of strategic work. But when you're trying to make a difference and impact the way that people are thinking about things on the ground, a bottom-up approach is more appropriate. There's a variety of different data sets that are collected by local communities to build these community wildfire protection plans. Here's an example of one for Nevada County that was developed in 2016 and later updated, where the community went through and they identified all their assets, you know, the things that they value, both man-made and natural, and they identified different fuel characteristics that were important for them to manage and mitigate, and they came up with a plan. So if you think about this top-down approach and this bottom-up approach, there's a bunch of data that's collected that we need to understand overall wildfire risk in a systematic fashion. You know, it's not just the built environment that's important, but different elements of conservation are important as well. And again, looking back at that landscape, if you're familiar with the Plumas area up by Quincy, where a lot of this community-based forestry first started, sometimes these different pillars are competitive in nature. A lot of times when you manage for one, you're managing for a lot of them. And they take in things into consideration like forest resilience, carbon sequestration, healthy fire on the landscape, harmful fire on the landscape, different human dimensions and water dimensions. And these characteristics, each one of these different elements could also provide a huge suite of data or information products that could be brought into our decision-making lens or decision-making framework that we need to think about. A lot of the stuff is dynamic in nature as well. So it's not like you're going to be able to create one layer for any of this stuff that's going to make a difference. It's going to be either reactive to different stressors that are external, or we could be proactive in terms of the way that we manage those different environments to actually take into consideration some of the things that we can't control, specifically fuel loads. And if you look at this, for example, where you have drought patterns that have occurred from 2016 to 2020, you can see that, hey, look, we know this drought's going to have a knock-on effect on fuels, and we can capture that information and integrate it into the way we think about wildfire risk. And the folks at Salah Sciences were able to do that with Earth observations and a variety of secondary data sets, including LIDAR and some field observations, to get an understanding of tree mortality, large fuel models that we could actually pull into our wildfire models and that we could layer in to some of these impact studies that we're interested in. So think of a secondary information flow that has knock-on effects from external drivers like drought, climate change, urban growth, those sorts of things. What's also interesting too is that a lot of these situations, you know, when we're thinking about this, some of them are naturally driven, some of them are anthropogenically driven, human driven, where, you know, fires are started by a wide variety of things, like lightning, like arson, like smoking, like power lines, so on and so forth. So we can get a better understanding of what causes those starts and how those starts change over time, or how we can manage those starts. It could really have a big change in terms of the way we think about measuring and monitoring impact at multiple scales. Here's an example where I have a map of that same map that we had in terms of where fire historically has occurred across the state of California. And then on the left-hand side, you see a map of utility sparked fires. And you can see that, you know, there's a relationship between it, because the thing that drives large wildfires, namely dry winds, hot dry winds, are the same sort of things that cause utility lines to spark. And so in that situation, we could really identify a data-driven approach where, well, we know where the ignitions potentially could be, we know what drives them, we know where they could be harmful. So let's see if we can start fusing those bits of information together on multiple scales to get a better measure of impact, not only for today, for tomorrow, but maybe for the next 50, 60 years. And then based off of that, go back to the ground and impact a variety of additional management activities, like we saw with the community wildfire protection plan, that we could actually document and ingest into a fuel modification layer that feeds the next round of measurement and monitoring. That's a lot of data. That's a lot of information products. That's a lot of things to think about, right? How do you pull all this stuff together? It's hard to pull all this stuff together. And there's a variety of different folks that are actually trying to do this. One example of this is the Pyrogens program. It's funded by the California Energy Commission. And its purpose is really trying to figure out how do we take all the different learnings at multiple scale for extreme fire weather and integrate it. Do the same sort of thing with fuel mapping, how to get a better characterization of what the fuel loads are on the landscape, and integrate it with integrate the field-based measures with lab-based measures to inform fire behavior models. And then use those two learnings from the first working group and that second working group to inform both near-term forecasting for impact, which is that third working group, the one that's in orange, and long-term measures of impact, which is our fourth working group in this scenario, which is led by the UC Mercer team. So think about the last one is how do you integrate this stuff for climate change assessments, fifth climate change assessment, that sort of thing. Let's take that third one and dig into it a little bit, because this will be an example of how you could fuse some of these data products together. So what we've done here, again, trying to take all those requirements and needs that I quickly blasted through in the first few minutes of this talk, and we put it into one place where we had information flows both from the field and from Earth observations, and we layered them in a place where you have a sandbox where you can start teeing them off from each other. And we broke it out by fuels, weather, overall risk, and measuring specific activities. When you look at the fuels layers, the idea here is that you could pull in standardized data sets from Landfire, which have a certain cadence with them. And then if you wanted to, you could pull in some information from the California Forest Observatory. This is one of the SALO-derived products that incorporate things like increased tree mortality. So you have the ability of actually pulling in live streams of what the fuel conditions are on the ground for your fire models. Connected to that, we're able to pull in the same sort of projections for fire weather. When you look at the fire weather indices that are shown here, there's a whole wide variety of them that are used for fire models. And each one of these layers has a temporal component to it. That's also important to take into consideration. So not only what is, in this case, the hot, dry, windy index today, but what is it going to be tomorrow and the day after, so on and so forth, as it interacts with all those different assets that you're actually worried about. From those, we're able to run the simulations, a variety of wildfire simulations using high compute environments where all these data sets are ready to go. And we're able to display a variety of different outputs. And if you think about that first slide that we talked about, there's a hazard layers, there's exposure layers that we're all able to pull into one spot, and you could actually play with them interactively in a quick environment. And this is opened up so the general community could have access to it. It's not put behind a paywall. It's completely democratized. So a variety of different local agencies, state agencies, local organizational groups could actually tap into it. And the idea is that you could actually play around with a bunch of learning. So going back to that conversation that we talked about with transmission lines, we know certain transmission lines are under threat. We could actually put them in here and we can get a live understanding of when that risk actually pops up and what we need to do about it. And again, here's one example of what this could potentially look like. This one is an actual live operation right now. In addition to that, you could, going back to the field, we can get situational awareness for active fires, projections of where fires are actually moving going forward in the next 5 days. Where are they going to actually be? And so in this example, the idea is that not only do we fuse where the fire perimeters are going to be over the next 5 days, but we could tap into local sets of information. Like in this example, this is the Alert Wildfire camera system, to tap in and see where the fires are actually physically located. So you could actually look at the live projection of where the fires are going to be, along with a real-time observation of where it really exists, and make these data sets available to the general public along with targeted community members to drive multiple scaled impacts. And so it's doable, right? But in order for us to be able to do this, things need to work together, right? We need to be able to organize and access a variety of different ground intelligence streams. Earth observations need to be processed and made available in a variety of different settings, both for fuels and weather. We need to be able to have access to high compute environments in order to make any of this stuff run in a meaningful way. Community wildfire-based models that are open to the community for testing and for validation and verification need to be accessible. And if we're able to do all of this stuff, we'll be able to deliver multiple scaled impacts for a wide variety of end users that are all feeding from the same information streams. It's a lot of information. I really appreciate your time here. If you have any questions, please let me know. Thank you.
Thank you so much, David. Great talk to wrap us up. I'd like to end by saying thank you to all our speakers today, Sander, Yifang, Ariana, and David, for sharing their work with us, and to all of you for joining us for today's program.